The title of this presentation is Quantum Information Processing, Odd Cycle Games, Topological Error Correction, the Mark Giant of Connected Components. To begin with a presentation overview, today we will discuss an upcoming archive preprint of mine that's going to appear soon that I'm going to submit next week, which is relating to parallel repetition for the odd cycle game, which shares connections with computing the surface areas of foams over the torus. And to make ourselves comfortable with parallel repetition for other quant game theoretic settings, we will provide an overview of expressions for the optimal value, bias, and optimality of the bias, as well as previous arguments due to the author myself that were used to characterize prospective quantum advantage for other games rather than just for the odd cycle game, and still, nevertheless, how there are a lot of similarities with performing topological error corrections as well as with the toric codes and the surface codes. And then we will introduce two references which are important for describing connections between parallel repetition and related problems, which are relating to aspects from computational geometry for minimizing the surface area foams. And altogether, we will conclude the presentation by providing a few probabilistic statements that are formalized in more detail in this upcoming archive preprint. And so the odd cycle game, in comparison to other quantum games that I've discussed on my YouTube channel earlier this year, can be analyzed through the phase shifted Bell state. The Bell state is typically a very important state that everyone is talking about when they're looking at quantum physics or quantum information theory, because it's very much allowing us to determine, so to speak, as I'll describe in a couple of slides, what's the minimal model of entanglement and how this can actually be related to EPR pairs and several other types of equivalent objects. And in this case, for the odd cycle game, the Bell state is a little bit different because it still shares in the similarities of having a 1 over square root of 2 normalization that typically appears when we're looking at other types of Bell states, because after all, we're just taking a superposition of two states, so we're normalizing by a square root of the number of measurements of their number of states. But we're also having an exponential of a phase, which is amounting to the fact that we're just basically phase shifting this part where this angle theta is taken to be over the unit circle, namely between 0 and 2 pi. So just basically modulo 2 pi. And what this actually is also relating to is that we're also having in the first term of this phase shifted Bell state a ket zero term that's taken with respect to Alice's system, namely Alice's zero element, as well as a ket one term that's taken with respect to Bob's system, namely Bob's ket one identity or his identity element, as well as just alternating the term in which the one and the zero ket states appear under the shifting term. And this is important because when Alice and Bob are formulating measurements in Hilbert space, when not only when they're playing the odd cycle game, but any type of quantum game, and they're trying to seek some type of prospective quantum advantage, this is important because they need to determine whether, well, basically they need to source all of their information, which are being used to construct the individual components from this phase-shifted Bell state from their Hilbert spaces, which are respectively given as C to the d sub a, namely a Hilbert space which has dimension to however many states Alice can use for her strategy, in addition to a Hilbert space C raised to the d sub b, namely relating to the Hilbert space, which has the dimension corresponding to whatever states Bob can use for his quantum strategy. So besides actually beginning this presentation by describing the phase-shifted Bell state, which we're going to further describe, I just wanted to very quickly present this because it's relating to one of the references from Oxford and University of Sevilla that I'm going to be further describing later on. But, however, irrespective of this phase-shifted Bell state that we presented in the previous slide, the referee scoring predicate for the odd cycle game still takes on a familiar form as it does for other quantum games. Namely, we're looking at a referee scoring predicate, which is a function v, and it's a function, and it's dependent upon little s and little t, namely the questions that the referee distributes to Alice and Bob, respectively, which are drawn uniformly at random from the referee's probability distribution, and is given by the condition that if the referee's scoring predicate, which again is the function of these two questions that he distributes to Alice and Bob, when it's multiplied by AB, namely the responses that Alice and Bob give, is this if this quantity, this object is identically one, if and only if Alice and Bob win, and otherwise it's -1 if and only if Alice and Bob lose. And so this is constructed from the product probability distribution of the referee pi over uh, the product S times T, namely the product of all questions that he can distribute to Alice and Bob. And this is important because the responses of Alice and Bob, depending upon the entangled state that they share, in which after sampling this pair, namely ST, which is distributed according to pi, the referee's probability distribution, after the referee sends one question S to Alice and another question T to Bob, like we had just mentioned. And in previous multiplayer game theoretic settings, one can examine the bias, which satisfies the following approximality condition. I'll provide more of an explicit representation for the bias, but it's just basically determining how, if Alice and Bob pick a certain strategy, they would deviate from optimality, and correspondingly, what would be their expected probability of being able to win a game of interest using quantum strategies. And this is given by the fact that this approximality condition given by the following statement, namely the following inequality, which is to say that if we fix some strictly positive epsilon parameter, we can look at a 1 minus epsilon multiplicative parameter multiplying the bias, which is serving as a lower bound for the summation in the middle part of this inequality, which is involving contributions over the summation over the possible questions, as well as a bra of an optimal strategy for playing the game using quantum strategies, as well as a tensor product over the players of their observables, or namely their answers, that Alice and Bob, or however many number of players in a multiplayer game theoretic setting, can offer when responding to the questions from the referee's probability distribution. And we're also looking at a ket of the optimal state of the optimal strategy, which is less than or equal to just beta sub g, namely the bias without the 1 minus epsilon multiplicative factor. And this type of approximality condition takes on a different type of aspect for the odd cycle game because, as I'll further describe, like I had alluded to for the viewers in the overview side, pretty much you have to take into account these topological and geometric characteristics, which are related to cycles, marked connected components of the giant, which are other types of objects which I'll describe, which can just basically be related to a tensor contraction mapping, which allows us to formulate several types of probabilistic statements. And taking the supremum over all possible strategies that Alice and Bob can use yields a bias dependent upon only the game itself. Namely, if we majorize or we take just the supremum over the possible strategies that Alice and Bob can make use of in their bias, it's just the bias beta sub g, just dependent upon the game itself, independently of the strategies that Alice and Bob can use. And EPR pairs are related to the minimal system for entanglement, like I had alluded the attention of the viewer to earlier. It's given by the fact that one can construct the EPR pairs by looking at just basically the tensor product of two operators, whereas the viewer can see on this slide, the first tensor product of operators can just be the identity with itself, or we can look at the second tensor product of identities, namely the sigma x, the poly x operator tensor product with identity, or even in the third EPR pair, the tensor product of the poly z operator sigma z with the identity, as well as also the product of the poly x and poly z operators with the identity. In the whole effect of constructing such a system is that it's very much allowing us to characterize what Einstein's so-called spooky action at a distance, in which just basically quantum mechanics and quantum physics allows for communication between particles or that are in seemingly far away or very distant locations from each other, which is going to relate to the prospective source of quantum advantage, which Alice and Bob can make use of for the odd cycle game. Namely, given the fact that by making use of entanglement, even though Alice and Bob are not directly communicating with one another, they can have some type of idea about how they can color the vertices of cycles they're looking to fill in from a certain pattern to satisfy the referee scoring predicate. And moreover, for the EPR pairs, these operators that I described for the viewer on the slide, these four collections of operators dependent upon the identity operation, the poly X and the poly Z operations, as well as the product of the poly X and the poly Z operations. It's given in terms of acting on a superposition, namely a superposition of the ket 0, 0 state plus the ket 1, 1 state normalized by square root of 2, which has the effect of obviously for the identity, for the tensor product, the identity with us, with itself, it just returns a state. Whereas when we're looking at the tensor product, the poly X operation with the identity, it's switching the occurrence of a 1 and a 0 in the first entry of these two kets, which are appearing in the superposition, as well as with the sigma Z operation, tensor product with the identity, it's switching the sign of the second ket state in the superposition. And finally, applying the sigma x and the sigma z, namely the poly x and the poly z operators simultaneously together, is having the simultaneous effect of switching a one, switching the occurrence of the first zero and the first one, as well as the sign of the second ket in the superposition. For the CX, sorry, I'm sorry. For the CHSH game, which is equivalent to the XOR game for two players, the optimal value can be expressed through the following optimization problem. Namely, the optimal value, which is corresponding to the maximum winning probability of the game when Alice and Bob use quantum strategies, admits the following representation. Namely, it's 1 over square root of 2, which is identically equal to a supremum over a sub I, b sub jk, and psi, where these terms that are appearing in the supremum are given, namely a sub I, namely the ith index of the tensor, which Alice is using to respond to a question that's drawn uniformly at random from the referee's probability distribution. And also we have another tensor b sub jk, namely for I not equal to j, because Alice and Bob can't respond to the same question that's drawn uniformly at random from the referee's probability distribution, which is given by the fact that Bob, when he's constructing his possible responses, he has to take into account all of the questions which Alice has not responded to, in addition to K, the second index corresponding to his possible responses to the questions, to the question drawn uniformly at random from the referee's probability distribution. And finally, the psi term is relating to the optimal strategy that Alice and Bob can use for winning the CHSH XOR game with quantum strategies. And this is given by the fact that we're looking at a normalization of 1 over 4 times little n choose 2, where this combinatorial factor appearing in this normalization is relating to the fact that there are a total number of n choose 2 ways for the referee to distribute little n questions to two players, namely to Alice and Bob. And we're also taking a summation, namely 1 less than or equal to I less than or equal to j less than or equal to n, namely a summation between I and j over the total number of questions that are contained within the referee's probability distribution, which is relating to kep psi in or bra psi and kep psi, while the middle part of this term appearing in this bra ket state is dependent upon a sub I b sub ij plus a sub j b sub ij plus a sub I b sub ji minus a sub j b sub ji. And it's important to note that in the superposition that's appearing in between this bra and ket state for the optimal state, we're having an anti-commuting term, which is relating to the term in which Alice and Bob basically using classical strategies would end up losing the CHSH XOR game, which would hence result in decreasing their winning probability. And even the structure of this term here is relating to the prospective quantum advantage, because it's a well-known fact that when Alice and Bob use classical strategies, they can win the CHSH XOR game 75% of the time, whereas with quantum strategies, they can win it 86% of the time, hence resulting in an 11% improvement using this entanglement in Einstein's spooky action at a distance. And the bias for two-player games takes the following form through a summation over bracket states, which is also dependent upon the tensor product of Alice and Bob's possible answers to the referee's questions, which is to say that that bias, which we had introduced earlier in terms of that approximality condition, is given in terms of the bias of G sub s, namely dependent upon the game and the set of all possible strategies that Alice and Bob can use respectively, which is equal to a summation over little s and little t, namely all possible questions that Alice can receive, where in addition to all possible questions that Bob can receive, which is given by G sub st, namely the game matrix, which is being multiplied by a bracket state, namely a Bob psi, with a tensor product of A sub s with B sub t, as well as a ket psi state. And as one can expect, given an arbitrary number of players, the optimal value and bias can be expressed as the following. Namely, if we're just looking to study multiplayer quantum games or with an arbitrary number of players, namely the NXOR game, like I had examined in my first archive preprint from earlier this year in May, we can straightforwardly generalize the bias and the optimal value from the CHSH XOR value that I provided and described for the viewer earlier in the slides, which is to say that omega n of XOR, which of G, which is equal to the optimal value of the n XOR game using quantum strategies, is proportional to 1 over a normalization of distributing little n questions to big N players, as well as taking a supremum over this psi of n XOR state, which is relating to a bra of a psi n XOR optimal strategy, as well as a ket of a psi n XOR optimal strategy in the script P term, which is relating to playing the term of taking the permutation. It's just basically like a permutation operator, like I'd described and alluded to for the viewer earlier, for the CHSH XOR game, in which pretty much you have either, as I've described and defined here, either a minus one raised to the indicator of winning the XOR game, or a minus one to the indicator of losing the XOR game, which is having the effect of just basically either having a one or a minus one sign corresponding to whether Alice and Bob win with probability either one or zero, given some quantum strategy. And furthermore, as one can expect, the n XOR bias is given in terms of beta n XOR G, which is relating to just, again, a normalization of one, the reciprocal of a combinatorial factor, little n, like all the possible ways for the referee to distribute little n questions to big N players, as well as a supremum of just now the game matrix for the n XOR game that's being multiplied by psi of n XOR, script p of XOR, ket of psi of n XOR. And now I'm going to describe a recent paper of the odd cycle game that was of great interest that I'd seen earlier in this year, several months ago, and that I thought would be interest to also provide some overview in terms of how the odd cycle game, again, is different from those topological and geometric characteristics from other quantum multiplayer games that I've been describing. And it's a reference that's titled Experimental Quantum Advantage in the Odd Cycle Game, and it's from a large group of authors from the University of Oxford and the University of Sevilla. And I thought that this paper, in comparison to some other papers in the literature that I'd been looking through at the time from in quantum information theory and quantum information processing, it was interesting because the authors of this the large group of authors in this study, they pretty much draw our attention to at the same time experimental and theoretical underpinnings of quantum physics that I'll be describing. And this is again relating, like I had just been describing, the experimental theoretical trade-off between the experimental, or sorry, maybe I shouldn't have said experimental twice, but that just basically the experimental and quantum winning probabilities of the odd cycle game. Because pretty much you can look at performing this type of experiment for any type of game, even though in an earlier slide I had mentioned for the viewer and the audience that there's been some observed 11% advantage for Alice and Bob making use of quantum strategies in comparison to classical strategies for winning the CHSH XOR games. You can really phrase and formulate similar types of questions for other quantum multiplayer or game theoretic settings, or even just other quantum games, including the odd cycle game, which is a two-player game. And this is given by the fact that the authors of this Oxford Sevilla study, they provide us with the observation that the ratio of omega experimental with omega quantum, namely omega x with omega q, is approximately 97.83%. So it's just basically saying what would be the difference between what is the best maximum winning probability that someone can obtain when Alice and Bob play the odd cycle game using experimental results in which they describe I'm not an expert in experiments, but they describe just basically a lot of photonic experiments. In photonic computation, it's very helpful in quantum computing because it doesn't have as much of a temperature constraint as other types of experimental platforms, which is why companies like Xanadu or other types of industrial players, they were pretty much talking about making use of quantum computation using photonics because it can be done at room temperature. But never mind, this is just relating to part of the experimental conditions that they're using for realizing this ratio of 97.8% from the theoretical prediction for the quantum value for the odd cycle game, as well as the experimental condition that they can realize. And moreover, this paper also placed constraints on the number of vertices in a cycle that Alice and Bob can color using quantum strategies. Because as I'll formally describe in a couple of slides, it's very important to have an idea about how many vertices would this study from Oxford Sevilla consider, which is to say that if we're looking to color the vertices of a cycle, namely if we're looking to color the vertices along the boundary of a circle, Alice and Bob are going to choose by coloring one of the vertices, and the winning condition from the referee scoring predicate is given by the fact that it's satisfied if and only if for all of the vertices of the cycle the colors are opposite. So somehow Alice and Bob have to make use of entanglement for not only determining what is the best color to assign to the first vertex, oh yeah, my apologies. Alice actually is first going to start out the game, and after which Bob and Alice are going to alternate coloring all of the other cycles of all the other vertices on the cycle. And this again is relating to the fact that in their paper, they're discussing the experimental advantage in the odd cycle game between 3 and 27 vertices of the cycle. And from this constraint on the total number of vertices of the cycle, they then have they then look to measure that experimental winning probability that had been motivating for the viewer. And this is relating to the fact that the total number of vertices n that Alice and Bob are going to color in this odd cycle game is announced before the start of the game. So just basically, Alice and Bob have some idea about however many number of vertices are going to be in the cycle, and then the referee is going to judge whether they win the game by applying his scoring predicate to groups of two, namely groups of two neighboring vertices, until he is able to apply his scoring predicate to all the vertices in the cycle. And I felt that from this paper, from the Oxford Sevilla paper, they had a very interesting and helpful and informative diagrammatic representation of the workflow for the odd cycle game that I just very briefly wanted to reproduce because it's just pretty much been honing in on a lot of the more mathematical and formal notation that I'd introduced for the viewer closer to the beginning of the presentation, which is to say that Alice and Bob, they're interacting with the referee and they want to be able to make use of strategization as well as sharing entanglement for being able to inform quantum advantage. And the referee is distributing the questions S and T to Alice and Bob respectively, from which Alice and Bob return A and B respectively to the referee. And so pretty much with respect to time, Alice and Bob are going to determine whether they can make use of some entanglement-based strategy for realizing prospective quantum advantage for the odd cycle game. And the authors of this paper also provided depiction of the classical versus quantum strategies for the odd cycle game, and in particular, how these types of strategies are different. So I also just wanted to very briefly reproduce this diagram from their paper because it's pretty much getting on a lot of comments that I was describing earlier in this presentation, namely given the fact that Alice and Bob, they want to make use of some prospective quantum advantage through entanglement through being able to enhance their probability of winning the game. And in this case, for the classical strategy, which is given in the first panel of the figure that I've reproduced from the Oxford Sevilla paper. They describe how basically a classical strategy can run into some pitfalls in which we can see that when we distribute a three cycle, namely a cycle with three vertices for Alice and Bob to color, if Alice colors the first vertice one color, there can have some type of contradiction or some type of roadblock to them satisfying the referee scoring predicate for winning the odd cycle game because these two vertices, 0 and 2, are the same color. Whereas we can encounter a similar situation for a cycle with five vertices because we can have these two vertices, 1 and 2, are not equal. They're not the same color, which is good. Those two vertices within the entire cycle so far would satisfy the referee scoring predicate. However, when we look at also the next side, 1 and 0, those two vertices also satisfy the referee scoring predicate. However, we have a contradiction between the vertices 0 and 4. But also, we would see that rather than these two vertices, all of the other vertices in this cycle for n is equal to 5 vertices, a five cycle, they satisfy the referee scoring predicate. And finally, we can also see that if we add two more vertices to the cycle, when we have n is equal to 7 vertices, the viewer can convince himself or herself that if you go around and look at pairwise, just basically pairwise groups of two of vertices along the perimeter of this circle for the seven cycle, all of the vertices satisfy the referee scoring predicate. In, however, except the vertices 0 and 6. And so this is demonstrating how Alice and Bob kind of, when they use classical strategies and they kind of close their eyes, so to speak, how they could encounter some types of difficulties because either the total number of vertices in a cycle could serve as a constraint to them being able to win the odd cycle game using a quantum strategy. And pretty much using quantum strategies, Alice and Bob can look to basically make use of similar types of expressions, but they can compute these angles alpha and in phi, which I'll define explicitly for the viewer on another slide, which is underpinning the experimental quantum advantage that's being described in this Oxford Sevilla paper, which is to say that Alice, if she knows some part of a vertex that Bob can color, which is part of the assignment that's appearing in the coloring of the vertices for the odd cycle game, she can actually be able to compute some type of angle, which is given by the fact that it's starting at the vertex that she wants to color, but it's going all the way around the cycle, but one more position longer than whatever vertex Bob would color. And these angles are actually very important to define, which I'll further describe for the viewer in the next slide, in which you can just basically see how by making use of this type of arrangement with these angles, Alice and Bob can make use of perspective quantum advantage, specifically like we've been describing through entanglement, to be able to win this odd cycle game through this coloring problem of vertices of cycles with a higher probability. And so, more explicitly, I wanted to define a little bit more formally how the referee scoring predicate and other types of just basically notation can be established for the odd cycle game, given the remarks that I'd established for the viewer earlier, which is to say that the referee is playing the following role when interacting with Alice and Bob in the odd cycle game, which is relating to the fact that the referee is choosing a vertex X, which is between 0 and little n minus 1 for Alice, namely if there are n vertices in the cycle for the odd cycle game, Alice can choose to color initially any one of the vertices 0 up to little n minus 1 in either the same vertex or an adjacent vertex y for Bob, namely, which is to say that Bob, if we're looking in the odd cycle game, if we're looking for Alice and Bob to color the vertices in a clockwise fashion, Alice will start and then Bob will start by coloring the next vertex, and then they will alternate until all of the colors of the vertices in the cycle have been determined. And Alice is outputting a color A, which is in 0, 1, as well as Bob is outputting a color B in 0, 1. So it's a binary assignment of colors for each one of the vertices which Alice and Bob can use. And they satisfy, which is that if X is equal to Y, namely if Alice and Bob color the same vertex, the color that they or if the two vertices are the same, the colors that Alice and Bob assign to each one of these such vertices are equal. Whereas if X and Y are neighboring, namely they're adjacent, namely they have absolute value norm, a little L1 norm distance which is equal to 1, the colors are not equal, they're opposite. And again, I wanted to describe how do the angles for the quantum strategies come into play, which is relating to, again, some of the topological parts and also even similarities with topological error correction, because after all, topological error correction from seminal work and of, basically industrial players like Google Quantum AI and those types of related key industrial players, they've just been basically describing topological error correction in terms of embedding some, in terms of obtaining some periodic embedding over the lattice into the torus, and how pretty much that relates to just basically this case that I'll further describe because you just basically are looking to perform some minimization of a computational geometry problem for the surface area of a foam over the torus. And so, but back to the angles that are appearing in the quantum strategy, which is relating to the outer circles are Alice's measurement setting, and the inner circles are Bob's measurement setting. So the viewer will recall from those figures that I reproduced from the Oxford Sevilla paper, they basically describe two concentric circles. One of the circles is corresponding to Alice's measurement angles, and the other circle that's outside of it is corresponding to Bob's measurement angles. And pretty much what is happening is that formally these angles are given by alpha sub x, namely the angle that Alice has associated with the vertex x of the cycle, which is equal to phi sub x minus pi over 2n. In this reciprocal of the 2n value, it's coming into play because the classical value of the odd cycle game is given in terms of explicitly 1 minus 1 over 2n, where little n again is the number of vertices which Alice and Bob color in the cycle. So it's really nice when we're establishing experiments and basically points of comparison between experimental optimal values and quantum optimal values, like I've been describing for the viewer in the Oxford, which are appearing in the Oxford Sevilla paper, how pretty much it's really great to have some type of analytical expression of the classical optimal value in the mind, namely 1 minus 1 over 2n. And also, the angles that Bob uses, beta sub y is equal to minus phi of y, where these phi of k terms, namely phi of x and phi of y terms, are given in terms of pi k times n minus 1 normalized by n, namely the total number of vertices in the cycle. And by making use of two angles, Alice and Bob implement a quantum strategy for the odd cycle game through the following measurement operation, namely a measurement operator which is relating to the fact that given an angle theta, the two outcome projected measurement is a measurement of theta, which is given in terms of an outer product of the theta with itself in the plus basis, corresponding to just basically Alice and Bob either coloring a vertex one color plus, as well as an outer product of theta with itself in the minus basis. And these eigenvectors are given in terms of just being expressed in terms of 1 over square root of 2 times a ket 0 state plus or minus e to the I theta of a ket 1 state. So this type of state which we're using in terms of formulating outer products is very closely related to the phase shifted belt state that I described for the viewer at the very beginning of the presentation. And Alice decides whether to color a vertex in the cycle based upon the following criteria. Namely, Alice is going to receive some vertex x. She's going to measure her qubit again in the basis that's defined by this angle alpha sub x from her angle, like how we had described from the figure in the Oxford Sevilla paper. And with the outcome being +1 or -1, which is respectively corresponding to whether Alice is describing or is making the decision to color a vertex either +1 or -1 color, she's going to or a 0 or 1 color, she's going to output the color A, which is equal to 0 if and only if the outcome is +1, and 1 if and only if the outcome is -1. And also, as one can expect, Bob decides whether to color the vertex in a cycle based upon the following criteria. Namely, he's going to receive a vertex y, he's going to make use of the measurement angle beta sub y, and he's going to map his outcome to the color B, which is equal to 0 if and only if the outcome is +1, and 1 if and only if the outcome is -1. And with a general understanding of the first reference, I also now wanted to discuss another reference, which is more relating to the surface area of round foams. is relating to the fact that it's a paper almost 20 years ago that's very intriguing as well because it's pretty much describing how odd cycle games can be related to cycle elimination problems, which I'll describe in a workflow that's provided by these authors. And the reference from these three authors is titled Understanding Parallel Repetition Requires Understanding Foams. And again, it's pretty much relating to a kind of counterintuitive type of aspect of this information processing task, especially in quantum physics, because basically it's relating to the fact that we can make use of just basically different types of ways to understand the odd cycle game through a computational geometry type of problem through just basically minimizing the surface area of foams over the square lattice and also how that relates to minimizing the surface area of foams over the torus. And so this is relating to the fact that the authors of the second reference provide the following diagram for discussing several computational problems that are equivalent to each other. So this is again really just kind of a grand tour de force, if you will, of how all these types of topics and aspects that I've been describing for the viewer are related, which is to say that we start with strong parallel repetition. And as a special case of strong parallel with repetition, we can look at extraparallel repetition, which is relating to performing parallel repetition in those CHSH XOR games I've been describing for the viewer. And in itself, within parallel repetition, we can obtain a special case through odd cycle parallel repetition, which can then be related to a series of computational problems related to odd cycle elimination, and finally, a foam problem. So just basically in this paper, the author provide several types of very useful and interesting objects which can use to establish this correspondence, which is to say that, again, if we look at a foam problem, this has some type of purported connection with a parallel repetition problem. And in my upcoming archive prement, I introduce foams in the following way. First, we can denote a foam F over Z2, which is just belonging to the faces over Z2, the faces of the lattice. And that's because a foam, it's pretty much like a soap foam or like a other type of foam. It's just a type of object that can be defined over the lattice and that we want to periodically embed over the torus, which is actually going to share in some type of similarities in terms of the setting that one looks at for topological error correction. However, now it's actually relating to the fact that it's more of a computational geometry type of problem, which is having connections with parallel repetition as well as with approximate and exact optimality when Alice and Bob are making use of quantum strategies for playing the odd cycle game or even other types of quantum games of interest. And equipped with this foam, we can formulate the following optimization problem for computing its surface area, namely that should be a supremum, or sorry, an infimum. The infimum of the surface area is given an infimum over the foam of the surface area of the foam, which is realized through the spanning set, namely a span over R2, which is relating to hexagons with two 120-degree angles. So just basically, it's given the fact that if we look at a way to minimize the surface area over R2 with foams, that can be obtained through hexagons with two 120-degree angles. So it's just basically two angles 120 degrees along the top and bottom of the hexagon, and then they're connected like that. So this is just a very simple geometric consequence of looking to perform this infimum from this computational geometry type of problem for being able to minimize the surface area of a foam of interest. And we know that the surface area over the triangular lattice can be minimized with hexagons, namely through the surjection phi, which is mapping from Z2 into T2, which shouldn't come as a surprise for the viewer because I've been trying to motivate and establish several types of connections in which we can periodically embed Z2 into the two-dimensional torus, namely the torus which has the vertex set and edge set, which are given by V sub T2 and E sub T2, respectively. And this is allowing us to periodically embed the above set of linear combinations over RT to over T2, namely from over the plane R2 to the two-dimensional torus. And straightforwardly, the spanning set for maximizing the surface area of the foam that is periodically embedded over T2 takes the form a span over T2 of the hexagons with these two 120-degree angles. So just basically, we're looking at just trying to minimize the surface area of a foam over the lattice and how this relates to a periodic embedding over the torus. and how this is relating to just basically periodically embedding the hexagons themselves that were minimizing the surface area over the lattice to over the torus. And the observation from the previous slide can equivalently be expressed through the following linear combination over the over the torus, or over or sorry, it's over the two-dimensional torus. This is a typo, but it's just basically taking a set of linear combinations of hexagons with two 120-degree angles. And for the periodic embeddings of Z2 to the two-dimensional torus, i.e. the torus with genus 1, which topologically corresponds to a donut, one can also study the expected number of edges, namely the expected number of edges over the torus where these edges are belonging to either cubes and sections which are having non-empty intersection with the tube. And the cube, sections, and tube are just basically topological objects that have been introduced from this 2007 reference because just basically the authors of this reference provide a quantification in terms of just the Mark giant of connected components that I'll further be describing closer to the end of the presentation for the viewer, and how this is just basically relating to the number of vertices which we expect to be unmarked, which are belonging to the giant. And the giant connected component is very much a term that's used in percolation theory because it's very much relating to just basically phenomena like coalescence and whether geodesics in past they all coalesce together or they all come together, or whether there could be another type of separation of geodesics or other types of related questions. And so the cycle elimination problem definition, which is the first definition that's given in my upcoming preprint, is given by the fact that we can define the vertex set over ZD, namely the d-dimensional lattice, in terms of just vertices such that the L infinity norm is equal to 1, as well as the edges, which is just given by the neighboring edges, namely the edges which have distance 1, from which one can introduce the cycle elimination problem, which is relating to one of those equivalent problems which I described for the viewers relating to parallel repetition and strong parallel repetition, because it's just basically given by the fact that we can look at all the vertices for which there exist edges in some strictly positive parameter delta, such that the probability is such that there exists a topological cycle without removing countably many vertices is strictly positive, namely strictly greater than 0, as well as the probability that there exists a topological cycle after having removed a delta fraction of vertices from the cycle is equal to 0. And pretty much these topological cycles that are given in this 2007 reference, it's pretty much taking the role in terms of pretty much those cycles and those types of sources of prospective quantum advantage through entanglement that can be obtained through that experimental advantage through the odd cycle paper through the Oxford Sevilla reference that I had given. So even though these papers are like 15 years or more apart, I thought that it was really interesting and a novel type of connection within the literature to actually describe how these topological properties and characteristics from the cycles which are appearing in instance from this definition of the cycle elimination problem can be related to optimality, whether exact or approximate, from some of the other quantum multiplayer games or quantum game theoretic settings that I've been examining this year. And as one can expect from that workflow, the authors from their 2007 reference, which had described how just basically there's a correspondence between a cycle elimination problem and an odd cycle elimination problem. As another definition, we can introduce an odd cycle elimination problem over the torus, which is very much relating to the fact that, again, we're looking at just basically a very similar set of conditions, which is given from the cycle elimination problem from the previous slide, except that now we're looking at that the probability that there exists an odd cycle after having removed a delta prime fraction of vertices from the cycle is 0. So pretty much the cycle elimination problem and the odd cycle elimination problem, they can be very closely or almost equivalently described or defined in terms of each other, just given the fact that it's either removing cycle or an odd cycle, which is relating to just straightforwardly the names of these two types of elimination problems. And so the odd cycle game scoring predicate is relating again to that type of expression which I provided for the viewer and described, which I just very briefly wanted to now formally define, which is relating to the fact that the referee scoring predicate for the odd cycle game, V of odd cycle, is equal to, namely, the direct sum, which is just given in terms of a sum modulo 2, just basically Alice's strategy at x, as well as Bob's strategy at x plus t, namely the total of x plus t, which is corresponding to just basically him making use of his angles like we had described, which are appearing in terms of the prospective source of quantum advantage for winning the odd cycle game with a higher probability, making use of entanglement. And just pretty much as is given in terms of identically being equal to, again, the ordinary addition between Alice's and Bob's strategy modulo 2, which is equal to t if and only if Alice and Bob win the game and zero otherwise. And again, this is just corresponding to the predicate over the tuple of strategies script t, which is equal to script s sub a and script s sub b, which is given in terms of just mapping from the from the from the from the from the sorry, from the vertices of the cycle into just basically a two outcome raised to the d, because Alice and Bob can basically color any one of the vertices in a cycle either 0 or 1. And again, this is given by the fact that Alice's strategy raised to the d power is equal to Bob's strategy raised to the d power, which is equal to x mod 2. And the tensor contraction mapping is coming into play because it's another type of object that I described and alluded for the viewer earlier on in the presentation. And it's just basically given by the fact that we can construct a mapping script T, which is given as being defined in terms of the edges over the torus, which is mapping in terms of a direct or a tensor product over the vertices over the torus, which is relating to the tensor product representations of Alice's and Bob answers. So this is pretty much allowing us to just basically shrink down or contract, hence tensor contraction mapping, the total number of tensors that Alice and Bob can use for constructing a strategy for the odd cycle game. And this type of mapping is very important because basically in the upcoming archive preprint, I relate it to a lot of types of conditions, probabilistic conditions, that is, and relate it to just basically properties of the unmarked giant connected component. So that was just pretty much, again, something else that I found was really interesting to try to formalize and to try to probabilistically characterize using these two references in the literature that had not been done previously. And this is given by the fact that the tensor contraction mapping is just given by also the mapping script of tensor contraction, which is given in terms of the edge set over the two-dimensional torus, namely the genus 1 torus, which is topologically corresponding to a donut, which is mapping it to the tensor product over the vertices of just basically the tensor product representations of Bob answers, and just basically modulo or just basically removing the tensor product representations of Alice and Bob answers, which cannot win the odd cycle game. And this is important because the viewer will recall that there can be certain types of roadblocks to using classical and even quantum strategies when Alice and Bob are coloring vertices of the odd cycle, in which if any one of these two neighboring vertices have the same color, the referee's scoring predicate will indicate that Alice and Bob lost the game. So just basically, we're trying to remove these tensor representations, which are corresponding to strategies that Alice and Bob can use for playing the odd cycle game, which would not make them successful at winning. And the marked giant connected components over the torus is given by the following definition, namely the marked giant connected component relative to tubes of the two-dimensional torus is given in terms of just a disjoint union over connected components as well as over tubes, where again, these tubes, like I've been describing for the viewers, they're just basically segments which can stretch along either degree of freedom over the torus, which is described further in my upcoming preprint. It is again relating to the fact that, like how it motivated for the viewer in previous studies within percolation theory, which have been describing connected components of the giant. In this instance, the marked connected component of the giant is given in terms of just the probability that the number of vertices in the connected component relative to the number of vertices in the tube, namely relative to the number of vertices of a subset of the two-dimensional torus, is approximately 95 over 100, which occurs with probability 1. which is corresponding to the marked connected components of the giant for the number of vertices in the connected components V of connected components relative to the number of vertices in a tube V of tube, which can be straightforwardly given by these two types of expressions, namely the number of vertices over the torus such that V has a non-empty intersection with the vertex belonging to a marked connected component contained within the tube over the torus, as well as the cardinality of the number of vertices in the tube, namely the vertices in the tube where V has a non-empty intersection with a vertex belonging to the interior and also to the boundary of the tube. In the probabilistic statement, one of them at least that I include is reflecting topological properties of the giant to the tensor contraction mapping, which is relating to theorem one. It's one of the main results in my paper, which is relating to several types of probabilistic statements, which is given by the fact that under the assumption that the number of marked vertices in the giant satisfies the above property, the probability of sampling a tensor contraction mapping, which is given by property three, that's given in my project, provided following definition 13 occurs with high probability, which is to say that with high probability, the event that there exists for all giant connected components, there exists a tensor contraction mapping such that epsilon sub 1 is strictly between 0 and 1, such that epsilon sub 1 and the reciprocal of epsilon sub 1 are just basically forming a strict inequality in terms of the supremum of Alice and Bob's quantum strategy of winning the odd cycle game normalized by the quantum value of the odd cycle game, where we're only using tensors that are appearing in the image of the tensor contraction mapping. So it's just basically looking at bounding this ratio of optimal values for the odd cycle game. And it's just basically saying that the probability of this event occurs with high probability, which is approximately 1, where again, we're defining this quantum value of the odd cycle game with a restriction of the contraction, which is corresponding to the maximum winning probability that Alice and Bob win the odd cycle game with two quantum strategies, given the constraint that they only make use of tensors under the image of the tensor contraction mapping. So it's again just trying to determine if we reflect upon some types of maybe conditions on the tensors that would be prohibitive to Alice and Bob winning the odd cycle game, would bounding this ratio, or namely the supremum of this quantum strategies that Alice and Bob can make use of for the odd cycle game, would there exist some parameters which could bound these types of this type of ratio of winning probabilities, and how that could be related to the marked giant connected component. And the following proposition was also interesting that I wanted to close out the presentation with before the concluding remarks, because it allows us to establish equivalences between several probabilistic quantities, namely the proposition expressing the above probabilities with probabilities relating to the surface areas over foams. And this is relating to the fact that I'd really been attempting to motivate for the viewer how can a computational problem with the surface area of foams be related to a parallel repetition problem from that type of correspondence from the 2007 reference from those three authors at Microsoft Research and other types of related institutions, and how that can be related to the perspective quantum advantage that was described in the Oxford Sevilla study, which is to say that the probability is such that for all marked giant connected components, there exists a foam tube in section such that there's strictly positive m as well as d is equal to 2, such that these four conditions simultaneously occur through the ratio holds up to a constant of a product of factors. So just basically what we're saying is that these four conditions can be used to relate just basically topological and geometric conditions and constraints from a foam tube in a section, and that we can just basically asymptotically relate these two ratios of probabilities that was given from the previous slide to each other, given some complicated product of factors that I'm not going to describe, is described in further detail in the preprint. And so the concluding remarks I wanted to end out the presentation is that we provided an overview of some of my previous work from earlier in the 2025 year. However, in comparison to previous analyses of parallel repetition, we drew the attention of the viewer to topological characteristics of odd cycles, in addition to how the marked giant connected component can be used to formulate probabilistic statements of interest. And more details on other related probabilistic statements are included in the upcoming archive preprint, which will be submitted soon. And thanks for listening.